Oh hi, didn't see you there. I'm Mr. French, your AP Stats teacher. It's time to play a game. We're gonna play a game called It's All Fun and Games Until that happens. These are the rules of the game. Miss French up there has a random number generator, a TI-84, and she's going to be generating a random number from 1 to 10. I'm going to sit in this chair, and I'm going to try to guess the number that's randomly generated by Miss French. If I do not get the number, I can continue on to the next round. So if I miss the number that she generated, I continue on to the next round. If I match the number that she has generated, the game is over, and this happens to me on my head. Ooh. Without further ado, let's get started and play It's All Fun and Games Until that happens.
Random number generation 1.
3.
Random number generation 2.
8.
Random number generation 3.
8.
Random number generation 4.
2.
Random number generation 5.
5.
Random number generation 6.
10. Oh!
Random number generation 7.
2.
Random number generation 8.
2.
Random number generation 9.
6.
Random number generation 10.
8.
Random number generation 11.
1.
Random number generation 12.
3.
Random number generation 13.
4.
Random number generation 15.
10.
Random number generation 16.
7.
Random number generation 18.
2.
Random number generation 19.
8. Today we're going to learn about geometric probabilities. Let's go ahead and get started. Holy smokes, welcome back. It's good to see you. Let's get into it. Thanks for being here. We're going to talk about something called geometric random variables. This is 6.3 day 7. We're going to skip day 6 in your rubric for those that are following along on the Google Classroom. We're going to skip the 6.3 day 6. It's not going to be assessed. So we're going to skip to day 7. This is about geometric random variables. Our goal for this lesson is to find probabilities involving geometric random variables. So it's fairly straightforward. We'll do a few examples. Let's take a look at 3 scenarios that are all defined as a geometric random variable setting or a geometric setting. So the first scenario, you roll a pair of dice until you get doubles. In basketball, you attempt a 3-point shot until you make one. And the third one, keep placing a $1 bet on the number 15 in roulette until you win. Can you think of a few characteristics that each of these scenarios have in common? You should probably notice that in all 3 of them, you're looking for something to happen eventually, right? So I'm gonna keep betting until this one thing happens. Once that thing happens, then each of these scenarios will stop. That's one big thing about a geometric random setting. You're just looking for your first success. A big difference between geometric variables and binomial random variables is a geometric random variable is looking only for the first success. A binomial random setting might be asking about 3 successes out of 5, but a geometric random variable is only looking for your first success. How long will it take to get the number 15 in roulette? How long will it take to roll doubles when you roll 2 die? How long will it take to make your first 3-pointer when you're practicing basketball? Let's go ahead and define a geometric setting. A geometric setting arises when we perform independent trials of the same chance process and record the number of trials it takes to get one success. On each trial, the probability P of success must be the same. Very, very similar to a binomial random setting. However, a big difference is you're looking for your first success, and there really isn't a set number of trials. I could keep shooting those 3-pointers forever. I could, shoot 100 3-pointers and miss them, or 1,000,000 3-pointers theoretically. So let's take a look at the example with the hose being sprayed. Let's define a random variable. So we'll say the random variable y is equal to the number of guesses before French gets sprayed. So let's find the probability of what you just noticed. If you didn't notice, it took 19 times for me to try to guess that. Well, I guess I wasn't trying to guess. I was trying to avoid the number. So I'm looking for the probability. If I define y as the number of guesses before French gets sprayed, I'm going to find the probability that y equals 19. You know what? I'm going to adjust this here. I don't like the word before. I'll say until. So it's the number of guesses until French gets sprayed. So it took 19 for me to get sprayed. So this is a geometric setting. I was guessing on a random number generator. Ms. French was up at the top of the lawn with a random number generator from 1 to 10. I didn't know, obviously, what the number was. I was just trying to avoid the number that she would generate. So if this was the case here, if I said 4, I would have gotten sprayed. It took 19 times for me to eventually guess the number that she generated. So my question is, what is the probability that this random variable would be 19, that it would take 19 guesses until I eventually got sprayed? Well, let's think of a few things. I'm looking for until the first thing, like the first success occurs. In a geometric random variable, each probability, very similar to a binomial setting, needs to be independent from the other. Meaning that just because, I missed the number 5 times in a row, that doesn't make it more likely. It was always a 1 in 10 chance that I would guess the number, which means that it was a 9 in 10 chance that I wouldn't guess the number. Essentially what happened was this. So it took a fail. 1, 2, 3, 4, 5, 6, 18. Okay. So that means when you watch the video, I had 18 failures. I failed 18 times. I didn't guess the number until a very first success was on the 19th. So if we think about this, each fail has a probability of 9 out of 10. So it was very, very likely I would not guess the number that she generated, right? Because that's only 1 out of 10. So each failure had a 9 out of 10. I want this and this and this and this and this. If I want a sequence of events to occur, we know that if you want a sequence of events, you multiply the probabilities, adjusting for any condition. So if probabilities change, then you do have to adjust the following probability, but that's not the case here because they're all independent from each other. So each of these failures is a 9 out of 10 chance. So each of these is a 9 out of 10 chance, and then the first success is a 1 out of 10. A much simpler way to write this is that you have to fail 18 times until you get your first success. And that probability, the probability of the thing that you just saw for it to take 19 times until I finally guess the number, is pretty small. This has a value of 0.015, or about a 1.5% chance. This is a geometric setting. Geometric settings, you're always looking for how long it takes to get your first success. So you'll see this is pretty common throughout. Let's take a look at another example. I don't know about you, but I've had a lot of time to do some yard work lately, especially this spring break. I did a lot of yard work, some pressure washing, also mowed the lawn. So here's an example about mowing the lawn. Let's say that I have a pretty cranky lawnmower. This lawnmower is pretty stubborn. And let's use that as our next example. We're gonna be pretty assumptious with our assumptions, but let's go ahead and try this as an example. So to start my old lawnmower, I have to pull a cord and hope for some luck. On any particular pole, let's assume that the mower has a 20% chance of starting. I'm gonna say let X equal the number of poles that French needs to start the mower. Okay? I'm going to say that the probability of success is 20%. So let's do this. Let's find the probability that our random variable is equal to what you just saw, 13. So in order to calculate this probability, this is geometric because we're looking for it to start. It wouldn't make sense for me to keep polling it starts and then stop it and try to do it again. So geometric is up until your first success. So just to start the mower, which means that if it started on the 13th try, it didn't start on the 12 before that. So if I were to write that out the long way, it would look like this. Now, you don't have to write it like that, but it just kind of gives me a place to start. So if the probability of success is 20%, that means that the probability of failure each of those times was 80%, because it's kind of an old mower. So instead, each of these has a probability of 0.8. I mean, I could even write that. And then the last one is a probability of 20%. Now, I want this sequence to occur. I'm not saying that I failed or I fail or I fail. This is and. So I want all of this to occur, a sequence of events, which means that I must multiply these probabilities. So the probability, it would take 13 times if I assume that the true probability of success is 20%, that it would take 13 pulls to get my mower started, is 80% to the 12th, because that's 80%, that's 12 failures at 80%, and then the last one is the success. This is a big difference from binomial probabilities because I'm not looking for the probability of one success out of 13. 13 is what it takes. And so this has a probability of about a 1.3% chance. 1.4. Let's do a few other examples like this. Let's play around, maybe not equal in number, but a few other things here. So I'm gonna keep the same, scissors. So let's do a trickier problem. So I mean, if I wanted to just play around, you know, let's say it took not 13 pulls, but more than that, it took like 17 pulls, then that would mean that, so if, you know, probability that x equals 17, so when it equals a number, we can just really play around with, there we go. So if it said 17, then that means I failed 16 times, and then I got my success on the last one. So you'll notice that that's always true for geometric probabilities, is that your probability of success always happens just once, and that's at the end. Let's do something where it doesn't equal a number, because I feel like that's going to be a little bit too easy. Let's say this. Let's say that's the probability that x takes at least 6 pulls. So this does say at least. I know some folks are kind of nervous, or some folks might, you know, just think about that for a second. If it takes at least 6 pulls, that means that that's the lowest it's going to be. So what is the probability that it could take 6 pulls or more, in other words? So I'm looking for the probability of at least 6 pulls. So that would include a lot of different scenarios. That would include 6 or 7 or 8 or 9 or 10 or 11. I mean, really, this is going to be equal to the probability that it took 6 pulls, or, remember, or statements, we add them. The probability that it could be 7 pulls, so it could take me 6 tries, or 7 tries, or 8 tries, or 9 tries, or 10 tries, or 11 tries, or ... That's not good, because theoretically it could, I mean, anything's possible. So it could take me 100 pulls or 1,000,000 pulls. If I want to find the probability of at least 6, this is not going to be helpful. Let me show you a picture of what probability distributions look like, and I feel like it should make a little bit of sense. In general, probabilities geometric probabilities have this shape. They start off kind of high. This is what a geometric probability distribution would look like. So like this is, you know, 1 pull, 2 pulls, 3 pulls, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So typically they look something like this, where, you know, if it's a 1 out of, it's like a 20% chance. If it's a 20% chance on the first pull, it has a 20% chance. On the second pull, it would have 20% of 20%, so on and so forth. Pretty much, as you keep looking at scenarios where you have to pull the cord more and more times, it becomes less and less likely it would take that many times. I mean, think about the probability that it took 13 pulls to get the mower started was a 1.3% chance. Think about the probability it would take 1,000,000 pulls for the mower to start. Well, that would be like minuscule. So geometric probabilities are always skewed right. They tail off towards the end because eventually the thing is going to happen. So the longer it takes for that thing to happen, remember we're looking for our first success, eventually that success will happen, and it's not going to take a super long time. And if it did take a super long time, that's why this probability is skewed right, because it's rarer as you consider the higher times it would take to get your first success. This is what I want you to think about. The probability of getting at least 6. So here's at least 6 right here. This is the probability we're looking for. And the problem with this is that it goes on forever, it goes off to infinity, it tends towards infinity. The better thing to look at is not this, but this. Because this stops. And probability distributions always add up to 100%. This infinite tail plus this needs to add up to 100%. So if we can find this instead, then we could just do, I'll call this, I don't know, call this whole area here, I'll call it star. If I could find this addition here, well then this is just going to be 1 minus star, because it needs to add up to 1. Let's go ahead and do that. So if I'm looking for the probability it takes at least 6 poles, that is equal to 1 minus the probability it would take 5 poles or less. So that's a accumulation of a few. So I'm going to find this probability. Well, that is, let's just find this first, and then we'll do the 1 minus. So this is the probability it would take 5 poles, which would mean that 5 poles would mean that you have 4 failures and then a success on your last, or 5 poles, or 4 or 3 or 2 or 1. So you'll notice I'm going to separate the or with an addition. So it could take 5 poles to get your success, or it could take 4 poles, which means you failed 3 times and then got success on the last one, or 3 attempts, or 2 attempts, or the very first attempt. And so I find all these probabilities, I'm going to add them together, these together. So if I add this big old string, take my time, especially with my parentheses, this adds up to about a 67% chance. So if I think about this right here is 67%. When I add up all of these, and so then this area here, the probability of at least 6 is the complement of 67%, or 33%. The probability would take at least 6 poles if I assume that the true probability is 20%, is equal to 1 minus 67%, which is about a 33% chance it would take at least 6 poles. And that kind of makes sense, because if the probability of success is 20%, that is 1 out of 5. And so the odds that it would take at least 6 should be more than 20%, because 6 is certainly more than 5. Let's look at a few examples of just identifying if it's geometric or not. Determine whether each of the following scenarios describes a geometric setting. If so, define an appropriate geometric random variable. First one, shuffle a standard deck of playing cards very well. Then turn over 1 card at a time from the top of the deck until you get an ace. This is not geometric because we are selecting cards without replacements. The trials are not independent from each other. So that's like very, very clear. I know with the lawnmower thing, we made a huge assumption, but it's a safe assumption. And it was for the sake of the problem. But in this one here, it's very clear that if you do not put the card back in the deck, that is certainly not independent trials. Here's the second one. Lawrence likes to shoot a bow and arrow in his free time. On any shot, he has about a 10% chance of hitting the bullseye. As a challenge one day, Lawrence decides to keep shooting until he gets a bullseye. Geometric or not? In this one, assuming his trials are independent, the probability of success is the same for each shot. It did say that there's a 10% probability on each shot. So in this case here, we are going to assume independence because they told us that the probability for each shot is 10%. So this is a geometric random variable, and the random variable should be defined as the number of shots needed to get a bullseye with a probability of 10%. That's pretty much it. Here is your suggested practice for geometric settings, and now what we're going to be doing is going on to reviewing for the AP Stats exam. A few announcements. The AP Stats exam is 45 minutes. It is going to be on the computer, and it's only free response questions. Big things to consider. If it's open note, open book, and 45 minutes with free response, that means that the questions are probably going to be pretty intensive. That means that, you know, it'd be nice if you got all your interpretations somewhere like a little index card if that's needed, but I would assume that we're going to get some pretty aggressive free response questions, because if you have an open note, open book test. That means that the AP College Board is going to be willing to give you much harder questions. So we actually are not going to be looking at very, definition-based questions, because you can just look those up in the book. That doesn't assess your knowledge of AP Stats. The best place to start our attention now is question 6s. Those are called investigative tasks. We have seen a few of them. I've actually given a few on your reviews before. We're going to start question 6 reviews. I do have a Desmos quiz for you to consider. That is posted on my class website right now as a task, so make sure you get that done so I can give you some feedback. On Friday, question 6 from last year's AP Stats completed. Take about 20 minutes, 25 minutes on it. It's pretty intense. Have a great day. Hope you enjoyed. Please comment back any questions you have in the comment in the Google Classroom, or you can shoot me an email and I'll answer you as well. Have a great rest of your day. I miss you guys like crazy. Thanks for watching. Hey, make sure you like and subscribe. Make sure I get those subscribers. Hopefully I can get a subscriber celebration video at 200 views. If you have an idea of something that you'd like me to do at 200 views, sorry, not 200 views. If you have an idea of something that you would like to see me do at 200 subscribers, let me know. We'll get it done. Have a good rest of your day. Thanks for thinking about some math. Until next time, this has been Mathing.
Let's get started.
That was perfect.